right, good morning. Welcome back. Hopefully you guys enjoyed the day off from chem class yesterday. Happy Friday. Here we go. We're back at the best class of the day. Hopefully you guys are ready to roll. Weather's starting to turn a little bit. Tomorrow's going to be really nice out. 50 degrees at least in temperature. Looks like there's some precipitation though. So there's going to be obviously some rain, probably not snow during the middle of the day, but maybe at night when it cools on down. We're at 32 degrees Fahrenheit. There's potential for snow. So there's I've never seen a forecast this big. Several days, but you could see what's ahead of us. It looks like that snow just about gone. I'm not a meteorologist. No. Could talk about some stuff with that. But anyways, here we go. So enjoy that day tomorrow. Go for a walk, go for a run, a jog. Huh? Haven't got much of phys ed in probably. So start establishing some sort of routine to get your body in check. Get yourself in shape. It's been like a whole year of you sitting at home. Maybe you've been working out, but my little heart to heart is you have one life to live. You have one body. You might as well take care of your body. The more fit, more active you are, the better your body's going to be to you as well. You'll be in better health shape as well. When your body starts to get overweight, you accumulate more fat, then your body, your systems have to work a little bit harder to survive, to sustain that fat. So take care of yourselves, take care of your body, find a nice diet, go for a nice little run, workout, establish a routine for maybe going for a walk the dog, go for a little jog, maybe half-mile jog. But that will make you mentally feel better as well. All right, so welcome back. Hopefully you're doing well. Let's check out a couple things. Let's check out the COVID update, see what happened when you guys had the day off yesterday from chem class. Right now we have 680 active cases of COVID in the county. Hasn't changed that much for a couple days. Resolved cases, there's 18,232 resolved cases of COVID. 390 deaths, hasn't changed in a few days. That is great news. Hopefully it doesn't change the rest of this pandemic. It would be nice if it didn't. Hospitalization numbers increased a little bit. 46 people in the hospital, 12 people in ICU. So that increased by a couple as well since the last time I saw you guys. You can check out the number of vaccines given out for Oneida County. And then let's check out this little daily positive test for Oneida County COVID. All right, so there's the entire pandemic for Oneida County. Checking it out. You guys are probably looking at, hopefully you're focused on over here. Check it out from a full screen. You can see a couple things there. We decreased really nice. We had a really good rate of decreasing from maybe end of January to about a week ago or so. So that decrease, I'm just trying to get the right colors here. From January 1st on, you saw this sharp decrease. It's still decreased to about there. But then the last week or two, we increased quite a bit. So you do see we had a nice low about a week ago or a week and a half ago, but now we're increasing a little bit. So that hopefully stays flat or decreases. If it increases again, like it did over here, if we see the same pattern from here to here, if we repeat this garbage, that's not gonna be good for us. So hopefully these numbers continue to balance out or decrease. What's going on here? More and more things are opening up. Why do we have more and more cases right now? More and more things are opening up. governor's starting to allow things to open up at a higher capacity. Cool. But you can see some things are affecting it. Athletics at some smaller schools are starting to be played. Basketball at smaller schools are being played. You're not wearing a mask when you play basketball. So that factor is going to spread the virus. When you guys come back to school, hopefully you come back to school, we're all wearing these masks. When you're playing basketball, you don't have to wear a mask. Which way are you going to spread more virus? I think you guys know that one. Another things that are affecting this, colleges are taking students back right now. Utica College, Oneonta. I'm not sure what MV is doing, honestly, with the routine. I'm sure some of you guys know. But anyways, Utica College actually was playing athletics, but they put a pause on that because they had a big influx of cases of COVID. So that, at the college level, is spreading more coronavirus. So we have to be smart as a community. When you take on the weekend, when you go for your jog this weekend, be smart, be safe. Go to Walmart, go shopping, whatever. Be smart, be safe. Sanitize that cart, wash that cart. Wear your mask correctly. When I say that, this is like my biggest pet peeve. When you put your mask on, it should go over the brim of over your nostril, and then below your chin. Boom. That's the look we're going for 2020 and 2021. Not like that. Yes, it's easy to breathe when it's below your nose, but those particles are going right into your respiratory system. All right, be smart, be safe. Go out, go for a run this weekend. Find a routine. All right, let's figure out what's happening in chem class for today. Best class of the day. Here we are. And we're back at it. Happy Friday. The quote of the week comes from Bernie Brown. Sometimes the bravest and most important thing you could do is just show up. Come to class, show up, put a little effort in, show on up. Thanks, Frank. The daily agenda for today, Friday, February 26, 2021. Today's a day 4. We're continuing on with kinetics and equilibrium, unit number 7. We are talking about potential energy diagrams. So these things behind me, we'll be making some potential energy diagrams, or we'll be leading up to these potential energy diagrams. So this curve right here, it kind of looks like the COVID curve, but it's not. It's a chemical reaction curve for either an exothermic reaction or an endothermic reaction. So over the next couple classes, we'll definitely go through, we'll make these reactions. You'll figure out how to do them. We'll go through some guided notes, we'll watch a flick. I'm going to hold off to the examples until topic number 3 is going to be done. So these assignments are not going to be assigned today. They'll be due next Saturday. All right. So let's figure out what's going on. Guided notes, let's get right to it. So right to the guided notes. Please open it on up. All right. So maybe you talked about this yesterday maybe text your friend about rates of reactions. Hi, Joe. Thanks for coming back. Peter died. There are 4 factors that affect the rate of reaction. 4 factors that speed up or slow down the rate of reaction. One is increase in temp or temperature. Concentration is a factor that affects the rate of reaction. Pressure for gases, and the last one is surface area. The 4 factors that affect the rate of reaction: temp, pressure, concentration, surface area. You should definitely know those 4 factors that affect the rate of reaction. If you want to speed up the rate of reaction, if you want the reaction to go a little bit quicker, what do? You have to increase the temp. If you increase the temp, these particles collide quicker, quicker, quicker. If you increase the pressure on gases, press on down to that pump, there's less space. There's going to be more collisions. That increases the rate of reaction. Increase the surface area. So if you take a big chunk, you break it on down to something smaller, that's going to dissolve or react quicker. And the last one, increase concentration. If you put more particles into a cylinder, it's going to speed up the rate of reaction as well. More collisions. If you want to decrease the rate of reaction, slow down the rate of reaction, you lower the temp, you lower the pressure, lower concentration, lower the surface area. Easy. Next thing I do want to talk about is these effective collisions. What's an effective collision? The collision theory. An effective collision has to have enough speed and orientation. So if two particles collide dead on or oriented correctly, that hits, then it's going to be part of an effective collision. They also have to have enough speed. So if these particles are going fast enough and colliding, that's going to make a quicker reaction rate. Those are effective collisions. We should definitely know all that from topic 1 and topic number 2. So here we go. Let's move on forward. We talked about kinetics and rates of reactions. You did the exit pass. If you didn't, it's due tomorrow. So kinetics is dealing with the rates of reactions. We talked about speeds of chemical reactions. In terms of effective collisions, definitely know what an effective collision is. We talked about the factors that affect the rate of reaction. We talked about concentration. We talked about temperature. Manipulating the temperature is going to change the rate of reaction. We talked about pressure. And we talked about surface area. Spent some time talking about those factors. We analyzed examples, and we also gave time for the exit pass. Definitely know the 4 factors that affect the rate of reaction. Now we're talking about some potential energy diagrams. So really quick, I guess it kind of looks like that, but not really. A potential energy diagram, I'm going to introduce it, but it's going to take some time before we get through all this topic and the next topic. You don't have to draw this. In a potential energy diagram, what happens is you have a chemical reaction. You have the reactant yields, forward reaction, the product. In a potential energy diagram, you're going to have reactants that happen first, and then they're going to be followed by the products, which would be in a different level. So you have reactants yield the products. There's nothing to write down here. I'm just introducing these potential energy diagrams. So reactant yields a product. When you go through that process, what happens? In order for the reactants to form the product, reactants to form this product, it has to go through a little cycle. It has to have effective collisions. Particles have to collide. Once they are done colliding, they're going to balance on off and form a product. So during this whole process here, you have effective collisions. So this portion of the curve, that's going to be my effective collisions. In a chemical reaction, you're going to have something called activation energy. That's the energy to make this reaction occur. This portion is called my activation energy. You're also going to have activated complex, which would be this portion right here. So activated complex, it gets to the top of the peak, and then it's going to balance off to the product. And then there's going to be something else there called heat of the reaction, which would be delta H, or it's the heat of the product minus the heat of the reactant. So all that stuff we'll highlight, we'll define. Hopefully we'll make this chart a little bit later in class as well. Did we go on a roller coaster ride yet last class? I don't recall. Did we take a ride on the roller coaster? No? All right. So I guess I'll start off with this first, and then we'll begin. Enjoy the ride. Okay, hopefully you enjoyed that little ride there. So why did I start off with a ride on the roller coaster from Cedar Point? Well, this class is going to feel like a little bit of a roller coaster ride, at least this time. Hopefully it's not.
I'm gonna stuff like, can you guys help me save my plane?
I thought someone was talking to me. Someone is talking to me, but I thought it was one of you guys. But anyways, this class hopefully doesn't feel like a roller coaster ride. Hopefully you have a good idea what's going on in this class. But that chart that we just analyzed, that potential energy diagram, is going to seem like a roller coaster. So let me just draw a couple things because we're going to be talking about energies quite a bit in this unit, this next topic or so. So in that roller coaster, what happened? There's a nice little roller coaster there that we took a ride together with. And it started off relatively flat. So we got on the roller coaster and it was relatively flat. And then as soon as like you hit a little straightaway, you go straight up that monster hill. Once we got to the top of the hill, it got pretty crazy. So you got to the top of the hill and then things started getting cray. You went down the hill and you went, woo, hands up, all this stuff. Maybe you went back up, maybe you went back down, maybe you did a loop-de-loop, but I'm just going to draw this one segment for now. All right, so in that roller coaster ride, we did a couple things. Let me throw a couple carts here with myself and you on the roller coaster ride together. It was a good time. So my roller coaster, there's my carts, couple wheels there. Cedar Point's in Ohio. Draw us on the cart. One, Mr. Brown, and there you are. Give you a couple more hairs than Mr. Brown. Mr. Brown's scared. There. All right, so anyways, here we go. Check out this roller coaster ride. We started at rest. We weren't moving. We're all locked into the roller coaster, and then we started to go uphill. So as we went uphill, what happened? You heard like the chains like lock you in. And we hear the click, 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 going up the roller coaster. That's locking it in so you don't fall back down that hill. So every roller coaster ride, most roller coaster rides, they're going to start off with an increase. If you went to Six Flags Darien Lake, you tried, or were on the Superman roller coaster, you're going straight uphill right from the get-go. Why? Because we want to increase our potential energy. Potential energy you heard about before, probably 8th grade science, probably before that. But potential energy is stored energy. As you go up this hill, you're increasing the amount of energy, stored energy, that you have. It's increasing its potential as you go up the hill. So potential energy at the top of this hill, potential energy is going to be high. It's at the highest point. So potential energy is energy in motion. So once you hit the top of that hill, you have a high potential energy. At the top of the hill, if you rode a roller coaster before, it's going to feel like you kind of like stop at the top of the hill. So once you're at the top of that hill, you get all the way up to the top of the hill, and then it's going to feel like you're at rest for like a second. Then you hit this free fall area where you're going pretty fast. So at that top of the hill, the kinetic energy, think about kinetic energy. Kinetic energy is energy in motion. At the top of the hill, you're not moving too fast. You're going up. You're switching directions. Kinetic energy is going to be low. So kinetic energy is low at the top of the hill. But then as you go down that hill, you're taking all that. So we need that energy at the top. So I go all the way up to the top. We need that energy to go through the entire ride of the roller coaster. That's why we start off high in the beginning of a roller coaster ride. So as you go down this hill, you're going faster, 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 faster. You get scared, then you hit like your stomach kind of like shifts a little bit at this point, or maybe it shifts at the top of the hill too. But at this point right here, that valley is when you're going to be going the fastest. So the lowest point at this portion, your kinetic energy and potential energy are going to shift. So potential energy, you lost all that stored energy. You're really low here. Potential energy is going to be low, but your kinetic energy, energy in motion, is going to be high. So it's a roller coaster ride is a constant switch between these energies. You never have more energy total than both of those combined. They just fluctuate back and forth, back and forth. This roller coaster ride is similar to what we're going to be talking about for potential energy diagrams. But let me just wrap up this roller coaster really quick. So once you get to this point of the roller coaster, you're obviously going to have enough energy to go through whatever obstacles maybe be in the way. So maybe it's a loop-de-loop, maybe it's a double loop-de-loop, maybe it's some more up and downs. But then once you get back at the beginning, it's going to start to flatten out again. And then there's the brakes. You're back to where you started. So you're back to velocity equals 0. Why am I talking about this roller coaster? Because these potential energy diagrams are really similar to this. On a potential energy diagram, you're going to have a start. There's my starting reactance. And then it's going to go through like a roller coaster ride. That's going to balance off to the final thing of a product. So this is kind of similar to a roller coaster ride. It's shifting its energies for sure, which we'll talk about specifically potential energy. All right, let's get back to class. Enough of that spiel. Enough of your drawing today, Mr. Brown. I want to learn about potential energy diagrams now. No more roller coaster rides. Let's go. All right, so here we go. In a potential energy diagram, be a lot of notes first half of class. There's going to be something called a catalyst. So a catalyst is something that's going to speed up the rate of reaction. A catalyst, you talked about this in biology class before. A catalyst are going to be substances that increase the reaction rate, the rate of reaction, that increase the rates of reaction by providing a different and easier pathway for the reaction. So a catalyst is going to be something that speeds up the rate of reaction. In a catalyst, when a catalyst is used, catalysts take part in a reaction, but they are unchanged. Catalysts take part in a reaction, but are unchanged when the reaction is complete. Definitely catalyst you should know. Something that speeds up the rate of reaction. A catalyst takes part in a reaction. When a catalyst takes part in a reaction, but they are unchanged when the reaction is complete. So I'll give you a quick visual. I'll give you a chance to copy this down. In a potential energy diagram, you have an x-axis, you have a y-axis. X-axis, y-axis. And then you're going to have a potential energy curve. Reactants yield the product. When a catalyst is added, it's going to speed up the rate of reaction. The reactant's the same, the product's the same. But when you have a catalyst, it's not going to get as high of a reaction. It's going to lower down to that. Catalyst speeds up rate of reaction because there's a different pathway in that one. So the green represents with a catalyst, the pink would be without a catalyst. I like to think of a catalyst as maybe you walk into school or you walking wherever, your friend's house. If you're walking to your friend's house or Proctor, here's Proctor High. Your house, we'll say, is right here. When you're walking to school, we'll go with that one now. Walking to school, you're taking this route, you're traveling west, you gotta go north for a second, take a long road to the left, you have to go north, and then go west again to your friend's house, pick your friend up, come on back, and then you have to go back to Proctor. So maybe that's your route to Proctor. You have a lot of streets you have to turn, can't walk through houses. This might be the traditional route you take. But if I asked you what's the quickest way to get to school, you could say, hey, it's going to be a straight line. What's the fastest way to get to two spots? It's going to be a straight line. So if you could get there as quick as possible by maybe hitting up a drone, if you jumped onto a drone, you could take a straight line there. So this is definitely, that blue line is definitely a quicker way to get to school rather than cutting through all the blocks. Or maybe you cut through all the neighbor's house and they got mad at you. Don't cut through yards. Straight line is definitely the quickest path. Kind of like a catalyst. Takes an alternative route. All right, catalyst lowers the activation energy. A catalyst is going to lower the activation energy of the reaction by providing a different pathway, reaction pathway. Alternative reaction pathway. Different reaction pathway. So it gives you a different pathway. And therefore increasing the speed of the reaction. So if you took the drone to school, yeah, you get there quicker. A catalyst is going to speed up the rate of reaction because it's not going to get as high. Make good decisions. All right, a catalyst lowers the activation energy. It's also going to lower something else. I'm going to throw something else in there too. It lowers the activation energy and activated complex. Activated complex. So yes, we don't know where these things are in the curve, but we definitely will. It lowers the activation energy in the activated complex by providing a different pathway for the reaction. Therefore, increasing the speed of the reaction. All right, once you're settled that, I will play a video on catalyst. I'll give you more time in a minute to copy that down.
In this video, you're going to learn what a catalyst is, how a catalyst works, and where catalysts are used in everyday life. Firstly, what is a catalyst? A catalyst is something which speeds up a chemical reaction, but at the end of the reaction has the same mass as it had at the beginning of the reaction. This means that it is not used up in the reaction. It must, however, take part in the reaction, or we might as well not have it there at all. So, how does a catalyst work? A catalyst works by providing an alternative pathway for the reaction to occur. This alternative pathway has a lower activation energy than the pathway without the catalyst. Here are the two pathways for a reaction. The blue pathway is the energy profile for the reaction without the catalyst, and the red pathway is the energy profile for the reaction with the catalyst. You can see here that with the catalyst the activation energy is lower. As a result of the activation energy being lower, there are more molecules with the required activation energy, and so more fruitful collisions occur per second, and hence the reaction is faster. Do you know where catalysts are used in everyday life? Most manufacturing processes are exothermic for economic reasons. The heat given out is used to maintain the operating temperature of the reaction. Exothermic reactions cannot run at too high temperatures as the yield will be too low. So, as we cannot increase the rate of these exothermic reactions by having the temperatures too high, we use catalysts to increase the rate of reaction. Here are two manufacturing processes that use catalysts. Firstly, the Haber process to manufacture ammonia, most of which is used in fertilizers. In this process, iron is the catalyst. The iron has potassium oxide, which acts as a promoter, added to increase its efficiency. And secondly, the contact process to manufacture sulfuric acid, which is used to make detergents and fertilizers. Vanadium 5 oxide, sometimes known as vanadium pentoxide, is the catalyst in the contact process. Catalysts are also used in catalytic converters in vehicles. These catalysts remove toxic exhaust gases by converting them into harmless products. So, to recap, catalysts speed up chemical reactions without themselves being used up. They work by lowering the activation energy and are used in the Haber process, the contact process, and in catalytic converters. Thank you.
Catalyst is something that speeds up the rate of reaction because it lowers the activation energy and activated complex. We'll label that probably next class, maybe this class. Potential energy diagrams, moving on forward. Those things we started off with, talking about that roller coaster ride. Chemical bonds contain potential chemical energy. Potential energy diagrams represent, they illustrate potential energy change. So PE change, potential energy change. That occurs during a chemical reaction. So every chemical reaction that occurs, what happens? There's effective collisions. Once you have those effective collisions, it's going through a chemical reaction. If you don't have enough effective collisions, the chemical reaction will not occur. So potential energy change that occurs during a chemical reaction. In a potential energy diagram, there's going to be a vertical axis, and there's going to be a horizontal axis. The vertical axis, up and down, we know that. The vertical axis represents potential energy. Potential energy. That's going to be measured in either joules or more like kilojoules probably, or calories. And the horizontal axis on the x-axis is going to be the rate of reaction. Horizontal axis, the x, is called reaction coordinates or rate of reaction. That could be in seconds. It could be in milliseconds. Could be in hours, depending on how long a chemical equation takes to occur. The progress of the reaction. The time it takes to go from reactant to the product. So this class is going to take some time to get through because there's a lot of terminology. But you'll know what these terms mean once we draw them on the curve. In order for a chemical reaction to occur, the reactants must have sufficient energy, enough energy to collide effectively. There must be enough effective collisions. oriented right, speed's right. In order for chemical reaction to occur, the reactants must have enough energy to collide effectively. If you have two atoms that never bond with each other, they're not going to react. If I have two noble gases here, stable octet, they're not going to react. If I have two things that have enough energy, that are oriented correctly, that collide, have enough energy, that will form a product. It's an effective collision. As reacting particles, this one reacts with this one, it's moving. These two are moving. They both have something called kinetic energy. Kinetic energy is energy in motion. These two particles have kinetic energy. Once these two things smash, it's converted to potential energy. So it does convert the energy, kind of like that roller coaster we talked about. As reactant particles approach each other, kinetic energy is converted. Kinetic energy is converted to potential energy. So there is a shift in energies. You take physics next year, you'll be talking about kinetic and potential a lot more. You might even take a free trip to Darien Lake, Six Flags. I think by next year, next May, things will definitely be back in order. So I would assume that's a perk of taking physics next year. Physics is a lot of math, but easy math. Good course to take for you guys. All right, potential energy. Dealing with these diagrams, so all this is really related to potential energy diagrams. Potential energy diagrams, the activated complex. Another portion of the curve is called the activated complex. With the activated complex, it's going to be temporary. Activated complex is temporary. So it's not going to stay at a complex for a long period of time. Things get complicated. Maybe they get complicated at home. Maybe you have a boo and things get complicated. You're not going to like that stress of being complicated for a long time. If you and your boo get in an argument, then you either A, resolve it, you could keep on fighting, then you're going to go crazy, or you say, see you later, don't need that stress in my life. Or maybe chemistry gets tough, it's complicated for a little bit, you might ask for help, you might figure it out by reading, understanding more questions, ask a friend, but then you'll get back to it. So complex doesn't last that long. If you had 5 tests in one day, you'd be stressed pretty much. It's complicated. You get 5 tests today, but then the next day it's gone. It's over with. Relieve that stress. All right, moving on forward. Chemical reaction. Activation energy is the amount of energy needed to form an activated complex or to start the reaction, Let me get rid of the last 3 words there. Activation energy, the energy needed to start the reaction. If you don't get this activation energy, then the reaction is never going to occur. If you don't get the activation energy, the particles are never going to collide. So maybe you can think of activation energy as you increase the temperature, as you increase the surface area, increase the pressure of the gas, increase concentration, that will start the reaction. And the last portion from potential energy diagrams on this page, talking about the heat of the reaction. Heat of the reaction, or delta H, or the change in heat. There's several different ways you can see this. This one we'll take next class. We'll definitely get to that one. the heat of the reaction, delta H. What's delta mean? It's a change in. Let me insert a symbol here. Special characteristic. I want a triangle. Delta H, change in. You don't have to put the triangle there if you don't want to. It's totally fine. Heat of the reaction, what does that mean again? It's the heat. It's the heat of the product. One moment, folks. All right, sorry, folks. All right, the heat of the reaction is going to be the heat of the product minus, subtracted by, the heat of the reactants. And again, we'll definitely get into that next time. We'll figure out how to solve for the heat of the reaction. We subtract. Heat of the reaction is a difference. Difference between the potential energy of the reactants, PE, and the potential energy of the products. I made a mistake. Potential energy of the products and potential energy of the reactants. Another teacher came in my room, threw me off for a second. All right, the heat of the reaction is a change of heat. That's the heat of the product minus the heat of the reactants. It's a difference of the potential energy of the product, potential energy of the reactants. We'll definitely see that. Okay, that is actually it for topic number 2, but we can't do the examples for topic number 2 because we haven't seen a potential energy diagram or labeled the potential energy diagram either. So I'm going to move on forward to topic number 3, which is exothermic and endothermic. And then once we finish the diagrams, we'll go through topic 2 examples, topic 3 examples, and then next week you should be able to do the exit passes on them as well. Does anybody need more time? Okay. Moving on forward to topic number 3, endothermic and exothermic reactions. Topic 3. They're very similar to each other, these topics. This one goes a little bit more further in detail. But we did talk about endothermic. We did talk about exothermic before. What's the difference between endo and exo? Exo means to release. So release, to leave. Bad choice of colors. Exo means to leave the room. You're exiting the room, you're leaving the room. Thermic is referring to heat. So exothermic, heat. Thermic, heat is leaving. Heat is leaving the system. Endothermic, there's your thermic again, heat. Endo means inside. So heat is being absorbed in that one. So we'll represent these potential energy diagrams in terms of exothermic and endothermic reactions. The first one up is going to be endothermic reaction. In an endothermic reaction, the product is going to be the product of the reaction. The product is, I got rid of some stuff. Did I? Oh. Sorry. All right. In a endothermic reaction, as, yeah, it's on the wrong page, as the activated complex changes to become a product, it will lose its energy. So it's going to lower, it's going to lose its energy. As the activated complex changes, It's going to lose its energy. And again, you're going to figure this out once we draw this curve. You'll see that. In an endothermic reaction again, I guess I'll highlight that so it pops out a little bit more. In an endothermic reaction, the product has more potential energy than the reactants. The reaction will become endothermic. So when the product is higher than the reactant, it's going to be an endothermic reaction. In an endothermic reaction, there's going to be more energy absorbed to form the activated complex. Than what was released to form the product. There's going to be a net gain. There will be a net gain of energy. I know I'm throwing a lot of terminology at you right now, but it will definitely make sense once we draw these curves. First day of this, a lot of terminology. Should be aware what they mean, but more, you should understand what they mean on the curve. The Regents will have at least 2 questions on this topic, these curves. The last thing for endothermic reaction, heat is going to form a positive value. So the heat of the reaction, or delta H, the heat of the reaction has a positive value. You subtract the 2 values for heat, it's going to form always a positive value. A lot of information for potential energy diagrams for endothermic reactions. Below, we'll draw one eventually. Before I draw it, I'm going to ask that we watch a video on exo and endothermic reactions. So try to think of these terms, see where they're incorporated throughout this video. Exo and endothermic reactions.
In this video, we are going to look at exothermic and endothermic reactions. So what are they? How are they different? What about their energy levels? In the next couple of minutes, you'll know everything you need to get started. An exothermic reaction gives off energy to the surroundings, like this fire giving off heat, whereas an endothermic reaction takes in energy from its surroundings, like this poor melting snowman taking in the heat. Just remember, exo means external, so giving out, and endo means internal, so taking in. Let's start by having a quick look. Because exothermic reactions transfer energy to the surroundings, and this energy is usually heat energy, they cause the surroundings to heat up, just like a bonfire, keeping everyone warm. Other examples of exothermic reactions are the neutralization reactions between acids and alkalis, the reactions between water and calcium oxide, and respiration. It is easy to detect exothermic reactions. Just get your thermometer and see if the temperature increases. Watch the hydrochloric acid and sodium hydroxide solution being mixed and see how the thermometer increases. Most chemical reactions are exothermic because heat is given out. Physical processes can also be endothermic or exothermic. When something freezes, it goes from liquid to solid. Bonds need to be made for this to happen. And to make bonds, you need to do some work. Thus energy is given out and freezing is exothermic. Similarly, when condensation happens, because a gas is going to liquid, again bonds need to be made, and so energy is given out. So freezing and condensation are both exothermic. Because in exothermic reactions, energy is given out to the surroundings. This means that energy of the reactants is higher, and the energy of the products, hence the energy curve for the exothermic reactions, will look like this. Now let's have a look at endothermic reactions. These are less common. Remember that endothermic reactions take in energy from the surroundings. Again, as with exothermic reactions, the energy being transferred is usually heat. So in endothermic reactions, the surroundings usually get colder. Again, we can detect endothermic reactions with a thermometer because the temperature would get colder. Some examples of endothermic reactions are electrolysis, the reaction between sodium carbonate and ethanoic acid, and photosynthesis. Endothermic reactions can also be seen in physical processes. When something melts, it goes from a solid to a liquid. For this to happen, bonds need to be broken. And to break bonds, energy needs to be put in, like our melting snowman. Boiling is also endothermic because energy needs to be put in to break the bonds for the liquid to turn to gas. Because in endothermic reactions energy is added to the reaction, the energy of the products is higher than the energy of the reactants. And so the energy curve looks like this. So there you have exothermic and endothermic reactions. All you need to remember is that exothermic reactions give out energy and endothermic reactions take in energy. Both can be detected with a thermometer. In exothermic reactions, the surroundings get hotter, and in endothermic reactions, the surroundings get colder. Exothermic reactions start with more energy and end with less, while endothermic reactions start with less energy and end with more. Freezing and condensation are exothermic because bonds need to be made, which gives out energy. Melting and boiling are endothermic because bonds are broken, which requires additional energy. Think of the snowman again. And finally, exothermic reactions are more common.
Okay, there's a little bit more insight on exothermic and endothermic reactions. Let's try to make a chart for this endothermic reaction. So this one chart that we will create will take us to probably the end of class. It's going to take some time. The first thing I'm going to ask that we do is, on this chart, I'm going to zoom out for a second. I'm going to actually get rid of this little box right here. If you want to create this on a separate piece of paper, it's going to look something like this. If you want to create this on a separate piece of paper, it'll be pretty easy to do. But I'm going to recreate this on my drawing pad. So I'm going to ask that you do it as well. I'm not going to copy and paste the image from the internet because once you guys actually draw it with me, it'll be more easily retained in your brain. So I'm going to suggest you do it with me as well. You can put it on a separate piece of paper if you really want to, if you don't want to deal with the Google Drawing app here. So the first thing I'm going to do is I'm going to highlight this little text box all the way to the right, and I'm just going to delete it, or right-click it with your mouse, or 2 fingers down on your keypad. I'm going to delete this whole column. I don't want this there anymore. If I were drawing this by hand, I would have had you guys put a number by it, but just delete that whole column. I need a little bit more space here to represent this diagram. All right, now I'm going to go through a couple things here. This is an endothermic reaction. In an endothermic reaction, nothing to copy down yet. In an endothermic reaction, you're going to have the reactant yields, forward reaction, the product. You have reactant to the product. That's a forward reaction. The reactant yields the product. I do have heat here as well. But anyways, in a chemical equation below, we have the reactant. Can't delete it. Did you click inside that text box? Right click inside that text box. So we have a reactant, which is 2 moles of SO3. plus a heat, which is 392 kilojoules, yields the product, which is going to be in this situation, O2 plus 2 moles of SO2. If you can't delete that box, it's not a huge deal. So again, reactant, product. Notice where my heat is on this equation. That kilojoules is a form of heat. It could be calories, it could be joules. That is a form of heat. It's on the reactant side. What's going to happen from an endothermic versus an exothermic reaction? The heat's going to be on the opposite side for an exothermic reaction. So that's one way you can figure out what kind of reaction it's going to be, exothermic or endo. Let me scroll down for a second. Oh, there it is. There's my heat. It's on the product side. That is an exothermic reaction. So a couple things to know. So what we're going to be drawing is a potential energy diagram for this chemical reaction. So we have 2 moles of SO3 yields with heat of new product. As long as we have enough effective collisions, it will move forward to make these products. If you don't have the effective collisions on the left, the reactant side, then this will never happen. As long as you have enough heat, so if we got the 390 kilojoules, if it didn't get to 392, then this would not happen. But we'll talk about it. We'll get there. All right, so once you're in this text box, I'm going to ask that you click on the text box and then insert drawing new. Here we go, more virtual drawing, digital drawing with Mr. Brown. All right, so you have that drawing pad. The first thing I'm going to do is make my x-axis and y-axis. Please take the line segment, and I'll put the x-axis horizontally. And my y-axis vertically. So on this little drawing pad, there's these little checker boxes, little squares there that you could use to help align yourself so it's straight. I'm going to thicken up these lines so it pops out. It's not letting you draw either. I'm not sure. Is anybody else having problems where they cannot draw? So Kai, I'd probably try to do it on a separate piece of paper for now. Maybe if you want to do it later and recreate it, you can. You could just upload it. I'm sorry, I don't know. Maybe you want to start fresh, refresh your screen. I don't know, maybe restart your computer. But I will be recording the class, and I will post it up there if you want to follow these steps a little bit later. Maybe I can help you out at the end of class. All right, so there's my x-axis, there's my y-axis. I'm going to label my axes. My x-axis is going to be rate of reaction. And I'm going to put just seconds here as my units. So time, the rate, how quick the reaction takes place. I'm going with seconds. It could be microseconds. It could be hours. It could be years for a reaction to occur. On the y-axis is going to be potential energy. And potential energy could be measured in kilojoules or joules or calories. So this is my y-axis. I'm going to rotate this around 90 degrees. I'm going to take the knob, click on the text box, take the knob at the top and just rotate it 90 degrees to 270. Probably doing some sine and cosine curves, I'm guessing, in class. That's 270. I almost went off on a tangent, but I'm not going to. No pun intended. All right, potential energy on the y-axis. And I'm going to give it a title up at the top as well. The title, I'm just going to take that chemical reaction that was on the last page at the top. I'm going to rewrite this chemical equation here just so we can make a connection a little bit easier. So in this reaction, it's going to be reactants plus heat yields the product. More specifically, this is going to be 2 moles of SO3, control comma, makes it a subscript value, plus your heat, which was 392 kJ, kilojoules, yields the product of O2 plus 2 moles of SO2. So I just want that just so I can really refer to this, make some connections once I draw that curve in. Reactant to product. What kind of chemical reaction is this? What kind of chemical reaction is this? What kind of chemical reaction is that in the pink? What kind of chemical reaction? That's acceptable. Yes. Maybe you want me to get rid of something. Maybe you want me to get rid of this. Maybe you want me to get rid of. You guys are a little stuck right here. Get rid of this right here. What kind of chemical reaction is that? Yes, Jumila, thank you. If I got rid of that right there, what kind of chemical reaction is that? So they ask you this question on the Regents. They want to know what kind of chemical reaction is that one in the pink. You could say it is an endothermic reaction because that heat's on the left side. If heat's on the left side, it's going to be an endothermic reaction. Heat's on the reactant side, endo. Or you could say, hey, it's a compound breaking down to 2 smaller things. It's a decomposition reaction as well. So endothermic reaction or decomposition reaction would work there. All right, so let's go through. Let's draw this reaction. I'm going to take a segment. No, I'm taking a curve. I'm going to take a curve here. And how this curve works out, I'm just going to play with it for a second. The curve works out if you click on a spot, and then if you click again, it's going to break up that segment. You click it again, it's going to just give you different angles. Every time you click it, changes the angles of the curve. So that's going to take a little time to really get down. But my curve line, I'm taking that curve. Maybe you have to practice with that a little bit. The curve, we're going to start off really low on potential energy. So I'm starting off low. I'm clicking on the y-axis. I'm dragging it out a little bit. I'm going to click again. That portion of my curve, that straight line, is going to be represented by the reactant. So that straight line so far, without me dragging it up or down, that straight line represents my reactant. What does that represent? It represents the 2 moles of SO3 and heat. That's my reactant. In this potential energy diagram, I'm going to move it on up. So it's going to be a flat line, and then I didn't really click off of this curve yet. I'll do this a couple times. It's tricky. And then I'm going to keep clicking it all the way to the top of this peak over here. So we're going to make it max out. It's going to get complicated. It's going to go to that high potential, and then it's going to balance out at the end. So it should look something similar to that. It's not going to look exactly like mine. Everybody's going to look a little bit different. That's cool. So it's going to look something similar to that. If you're drawing on a piece of paper, try your best to make it look similar. What did I just do there again? I grabbed my curve line, curve, And with that, I made a segment that was straight in the bottom. And then I kept clicking all the way to the top of this little mountain here, top of the roller coaster. Took that roller coaster ride in being in class. Then a straight line at the end. I think if you double click it, it saves it. That's a nice one. I can't redo it because that one came up too nice. I'm not going to redo it again. It should look something similar to that. I'm going to thicken it on up. Take your time to make it look similar to this. If you see a curve like this, it's going to represent an endothermic reaction all the time. You see it looks like this, endothermic reaction. I'm going to change the color of my curve just so it pops out at you guys a little bit more. Purple. Does anybody need more time in making this curve? Please let me know if you do, because we're going to be labeling this a lot. Kind of like behind me. All right. Guessing your tech skills are getting a little bit better. Good for you. I just discovered this curve last class, so I'm figuring things out little by little too. All right, next up, this represents a chemical reaction. In this reaction, please don't put this down yet. In this reaction, you're going to have the reactants, which would be indicated by this portion. And then you're going to have the products, which are going to be indicated by this portion of the curve. So here we go. Let's label this. I'm going to put a text box here. Text box. And then right above that line, I'm just going to say, hey, that's my reactants. And I'm also going to put what is in that reactants. So that's my reactant. And inside this reactant is going to be 2 moles of SO3. I guess you could do the heat too, plus 392. So that flat line of the reaction represents the reactant. That is my reactant. So I went a little crazy. I labeled everything this blue color. That's all my reactants. Reactant, reactant, reactant. Flat line is a reactant. Easy. It always starts off with a chemical reaction. Reactant to product. The first thing you have is the reactant. The last thing you have is going to be the product. So my product's going to be outlined this flat portion right here. Reactant to product. I'm going to take another text box right there and label this product. What's in this product? This can be O2 plus 2 moles of SO2. I'll color code this a different color as well. So that would be the product in this equation, in this reaction, this roller coaster ride. That's my product. So we know a reactant forms to a product if there's enough effective collisions. If you don't have enough effective collisions, it's not going to happen. This reaction had enough effective collisions. All right, reactant to product. That's the first thing you should be able to do. You should be able to look at this chemical equation and say, oh, my reactant is lower than my product. Yes, reactant is lower than my product. Whenever the reactant is lower than the product, then it's going to be an endothermic reaction. What's going to happen is you're going to have another curve that's going to look like this. The reactant's going to be higher than the product. That would be an exothermic reaction. But the reactant's lower than the product, that's going to be an endothermic reaction. Let's label some more things on this curve. Next thing up would be the potential energy of the reactants. Oh, the potential energy of the reactants, that's easy. Potential energy of the reactants is going to look something like this. That's my potential energy of the reactants. I'm taking another segment, line segment. And I'm going from the top of the reactant line all the way to the bottom to my x-axis. This interval represents PE of the reactants. I thicken it up, going green. I'm going to label it with a text box. This is my potential energy. I think we know PE is potential energy. PE of the reactant. Potential energy of the reactant. Easy. The top of that line to the bottom, potential energy of the reactant. Nothing too crazy there. The second interval I'm going to indicate goes from the top of the product to the bottom of that line. This is my potential energy of my product. So these portions of the curve you should definitely be aware of. The Regents, they love asking questions. What's this segment represent? So you should be able to know all these segments. You should be able to label them. It hasn't been too crazy yet. So potential energy of the product. Beautiful. All right, potential energy of the product. Easy. If anybody needs more time, please let me know. Guess I'm not going to finish this whole curve today. Next portion, last portion I'm going to label here is the activation energy. The activation energy is the energy needed to start the reaction. So its start has to go from the start, and it's going to go all the way to the top. So if you have this activation energy, then the product will be formed. So it goes from the start reactant to the top of that peak. Hopefully you can see it's going to the top of that peak. This is going to be called the activation energy. The energy needed to start the reaction. I'll label it orange. This is my activation energy. AE. Activation energy. And once you have that last one labeled right there, I'm not going to go any further. I know there's like 6 minutes of class left. Well, I want you guys to be able to copy this down and not feel crammed for your next class. So again, this is an endothermic reaction. The reactant is lower than the product. It's going to increase energy to the activation energy. Then it's going to flatten back on down. There's a few more things we'll put in here, but we'll do that Monday's class. So that's it for today. Have a great day. Make good decisions. Stay healthy. Stay safe. Enjoy your weekend. Go for a walk outside. Go for a run. See ya. Have a good one, guys. Bye, Kai. Have a great day. Bye, Jumila. Have a good weekend. Bye, Kim. Bye, Nadina. John, have a good one. See you, Steve. Go for a bike. How about a bike ride? A little slippery for that still. All right, guys. See you later. Have a great day. If you have questions, please feel free to ask.